Hi there, chemistry. I want to give you a pretty short introduction here to Lewis dot diagrams. So these are new to us, but you might have dealt with them in other science classes, maybe earlier in high school, maybe in middle school. Um, but dot diagrams are practical for certain reasons, but they are also related to the Bohr model. So we've been dealing with the Bohr model. You have yourself drawn out the Bohr model for the first 18 elements. I want to take that information and show you where the Lewis dot diagram comes from that information. Before we do that, I want to just talk about two terms that become pretty important to us here as we move into looking at the periodic table, and then we move into bonding and reactions. These two terms are going to kind of stay with us, so I want to take a minute and just talk through them. So as you look at these diagrams, we can look at neon, for example. As you look at these diagrams, you start to notice that the bigger they get, the more intricate the inside becomes. And that's the distinction that I want to draw. I want you to look at these Bohr models and see the inside electronic structure and the outer electronic structure. So if we're looking at neon, notice that the electrons and the structure of those electrons in the middle are just two, right? So the inner electrons, for neon, there are two of them. Now we have another term for inner electrons, and that would be core. So the core electrons for neon consist of those two electrons. So these inner electrons are going to be all the electrons except for the outermost ring. Notice, okay, for helium, notice helium has no core electrons, and neither does hydrogen. Neon has two core electrons. Look at the row that neon is in. What do you notice about all of the atoms inside that row? Right, they all have two core electrons. Every single one of those atoms has two core electrons. How many core electrons does every atom have in the third row? Okay, so hopefully you've noticed that you have the two on that first ring, and then you have 8 on the second ring. Every atom inside this third period or this third row has 10 core electrons. So it's an interesting thing that we start to notice. We start to notice the cores of these electrons, of these atoms within one row or one period are very, very consistent. And that's going to lead to some patterns of reactivity that we're going to look at in the future. Okay, the other thing I want you to notice, so compared to the core electrons, are those outermost electrons. So take a minute and look at the periodic table and see if you can find any patterns in the outermost electrons. Okay, now those outermost electrons have a name too. So the outer electrons we're going to call them valence electrons. So we have core electrons on the inside, and then that outermost ring is called the valence electrons. And notice that in a row, those valence electrons always increase by 1. In a column, notice that the outermost electrons are very consistent. In this first column, which we can also call a family, every single atom has 1 valence electron. In this second column or family, every single electron has 2 valence electrons, and so on and so forth. So the Bohr model, again, these patterns are going to come back to us when we start to talk about reactivity more after we talk about the periodic table, but definitely good patterns to see. Now, the Bohr model is really useful. The Bohr model can show us a lot. It can show us this pattern in the core electrons. It can show us the patterns in the valence electrons. It can show us other patterns too, like size, or some other patterns that we're going to talk about in the future, like electronegativity. There's a lot of good uses for the Bohr model. So once we make this chart, I really want you to keep this chart because we're going to refer back to it over and over and over again for the next couple chapters. So this chart is going to become precious to you. Please hang on to it. Please don't lose it. Please don't have to write it again. Now, the Bohr model, it can be very useful, but the Bohr model is also very bulky. It's really big to write. It takes up a lot of space and it takes up a lot of time. So sometimes we don't want to look at the entire atom. Sometimes we just want to look at the valence electrons. And this is where the Lewis dot diagrams come into play, because the Lewis dot diagrams is a way of diagramming only the outermost electrons, diagramming only the valence electrons. So it becomes more practical, it's faster, it takes up less space, and it shows us only the outermost electrons. Now, the valence electrons, or those outermost electrons, are really important because they drive a lot of how an atom reacts. And so we rely heavily on Lewis dot diagrams to help us understand these reactions. So we're going to talk about how to write a Lewis dot diagram for an atom. Again, this is probably something you've done before, so we're going to go kind of quickly through this, but this is definitely something you need to be able to do. If I give you an element off the periodic table, like gallium, for example, you should be able to draw the Lewis dot diagram for gallium. So let's talk about how to do that. If we're looking at the Bohr model for sodium, for example, a Lewis dot diagram is going to consist of the symbol of that atom and only the valence electron. So notice that sodium has 1 valence electron. I am going to put 1 dot around it. So for Lewis dot diagrams, you're only drawing valence electrons. Okay, you're also going to include the symbol, but you're going to draw the valence electrons as dots around the symbol. Now, as we get more and more valence electrons, there's a couple more rules you have to know. We're going to draw these dots as if they exist on a box around the symbol. So the Lewis dot diagrams can either be drawn on, they can be drawn on any of these sides, but they have to be drawn on the flat side. So if you have 2 electrons, they're going to both go on the flat side. You don't want to draw these in a ring like we drew the Bohr models. No rings. Also, another thing you want to know is electrons are going to spread out if they can. So if you have multiple electrons, you're going to spread those out on the sides. Okay, so for magnesium, for example, if we were to draw the 2 electrons that magnesium has, we draw 1 electron here on one side, we draw the second electron on the other side. Again, spread them out if you can. So aluminum has 3, we're going to draw the 3 dots and spread them out on 3 of the sides. Silicone has 4, we're going to draw 4 dots and spread them out on the 4 sides. Now phosphorus has 5 valence electrons. So you're going to draw the first 4 just like we drew silicones, but when you draw that 5th electron, you're going to have to put it on one of the sides with one of the other electrons. So in this case, once you have 5 or more electrons, you're going to have to start pairing them. And that's how electrons actually exist. As you get more and more electrons and they start to fill up some of these energy levels, the electrons do naturally fall into pairs of electrons. And we're going to talk a little bit more about that in chemistry. If you take AP chemistry, we're going to talk a lot more about that. Okay, so phosphorus would have 2 electrons paired. Sulfur is going to have 6. So 1, 2, 3, 4, 5 is going to pair, 6 is going to pair. So this would be a good time to pause the video, draw chlorine and argon's Lewis dot structure, and then come back and we'll do it together. All right, chlorine's going to have 7. 1, 2, 3, 4. 5 is going to pair. 6 is going to pair. 7 is going to pair. And then argon, 1, 2, 3, 4. 5 will pair, 6 will pair, 7 will pair, 8 will pair. Notice argon is almost, well, I'm not going to say it's perfectly drawn because it's not, but argon is perfectly completed. Every single electron is paired around argon. And again, that's going to come with some patterns and some implications for reactivity. You may already know a little bit about this family in the 8A column. You may already know the name of the family, and you probably, if you know the name of the family, you probably also know how that family reacts. So we will continue talking about this and more patterns that we see off the periodic table. For now, what I want you to do is draw the Lewis dot diagrams for the second row and also for the first row, and notice, do you see any patterns? All right, let me know if you have questions. I will see you in class.